Okay, so let's take a look at the way in which the structure of crystals are measured. So how do we determine the placement of atoms in new crystal structures? How do we determine the distances between planes? And so I'm going to just show you a simple technique, and this is going to help us to determine the separation between crystal planes. And so here what we have is a set of crystal planes that are shown. This is just a slice through them, so these planes would be coming in and out of the board. And so maybe this set of planes I have here is some orientation, like maybe it's a 110 set of planes, for example. And then this would be the spacing to the parallel 110. And so these are all 110 type planes, again coming in and out of the board. Right, and so I want the D spacing of the 110 set of planes. So what I could do if I was to shine an X-ray beam on the surface, so this is my incident beam coming in, is there's a special angle at which the incident beam will reflect off of, say, this top plane and the second plane, and it will reflect in such a way that the beam coming out is in complete registry or coherence. Okay. Well, this can only happen if this extra distance you see here in the green, this extra distance is equal to a multiple of this wavelength. Right. So if that extra distance there is not a multiple of the wavelength, then these beams, the diffracted beams, will not be coherent, and they will destructively interfere, and we will get no signal. Okay, because there's many, many more beams hitting the surface than just these two that's shown in this kind of picture. So what is this distance here? Well, given the D spacing there, that's D sine of this angle theta, this incident angle theta, okay, just from the geometry of this. And then this outgoing extra piece is also D sine theta. And so what we want is that total distance, which is 2D sine theta, to be a multiple of the wavelength, lambda. And so that's the condition for diffraction. Okay? So if we have a different set of planes that have a different spacing, a D spacing, then we will get a different angle for those. Okay? And in all of our measurements, we're going to just let n equal 1, and that just means it's a first order reflection. And that's the case that's shown here in this picture. So we're not worried about a beam coming in and reflecting off of the third layer, for example, and how it interferes coherently with the first plane. That would be twice the D spacing. So those types of signals tend to be very, very small. The main signal we get is this first order reflection. Okay, so let's go ahead and take a look then at what a pattern might look like if we were to scan the diffraction angle theta. And on these diagrams here, just notice that the diffraction angle is defined as 2 theta. Okay, so the incident angle you can see here is theta, but the way that this is defined, the diffraction angle is actually 2 theta. So we just need to be careful of that. All right, so here's a diffraction pattern of tungsten, which is body-centered cubic. And we're given the X-ray wavelength for the beam coming in. And in this particular case, we're given the radius of the tungsten atom. Okay, so what we'd like to try and do is see if we can figure out what plane corresponds to this 40-degree diffraction angle, or theta equals 20 degrees. Okay, so each of these peaks on here represent different planes in the structure, and those planes that are diffracting at these angles are from different D spacings, and then those D spacings have to all be consistent with a body-centered cubic structure. And that's how we can kind of back calculate what the structure is. All right, so we're going to take a look at this first peak here that was theta equal 20 degrees. So two more pieces of information we need, and that is in the cubic system we can find that the plane spacing is given by this equation here, where A is the cube edge length, and then the HKL are those Miller indices. So for example, 110. Also from the Bragg law, we have that the D spacing, if I just rearrange, is equal to n lambda over 2 sine theta. So we can go ahead and set these two equal to each other. Sorry. So we'll set these two equal to each other, and then we're going to rearrange to solve for h squared k squared l squared. That's what we're trying to find. Okay. The other thing that we know is that for the body-centered cubic, we know that the edge length is given as 4r over the square root of 3. So hopefully you already saw this in the other lectures. Again, n equals 1 for the first order. We're given the wavelength lambda. And we said we're going to look at this first peak here, 2 theta equals 40 degrees. So let's rearrange it to solve for the h squared k squared l squared. So that's what we've done here and substituted in all of our values. All right. So let's go ahead and plug in those values, and we'll get that the h squared, k squared, l squared, those Miller indices have to equal approximately 1.97. Okay. There's a little error there because partly in picking this peak, this is not exactly on 40 degrees. Okay. We approximated it as 40, but it's slightly off of that, but pretty darn close. If we were to pick this peak position exactly, then we would find that this number is 2. Okay. This h squared k squared l squared, when we find this quantity, it has to be an integer. So that's how we know that this is really 2. We interpret it as 2. It has to be an integer because remember in the Miller indices HKL, each of those is an integer. That's how it's defined. Okay. So we want to find the HKL, which plane corresponds to that first peak. We have the fact that h squared k squared l squared is equal to 2. And this gives us that the plane has got to be the 110. Okay. It looks like we've got 3 variables, right? And we have one equation. But again, we know that the HKL are integers. And so there's only certain combinations that we have to try. Right? So I mean, if we tried 100, well, those add up to be 1. Right? If I tried 111, those add up to be 3. So it's only planes like 101, 110, 011, right? Those are the ones that add up to 2. And these are all equivalent planes. So it doesn't matter which one I pick to label this. Those, again, are all equivalent planes. They belong to the same family. They're identical in the structure. And so we do have enough to go ahead and label that as the 110. And so we could do the same thing for the other planes, and we would come up with all of the plane indices for those different directions. I should say that in some cases, when you get a pattern like this, if you were to go through all of the different planes that are in the structure, that you might find that there should be a peak somewhere in the pattern and it's missing. And that is the case when we start taking into account the actual positions of atoms on the plane, which is really beyond this class, but when you get to crystallography, you will take a look at that. It's called a structure factor, and that will eliminate some planes. It's not going to add any new planes, but it will eliminate some. So that's just a little extra complication. All right, so that's Bragg's law, and I hope that that makes sense.